Welcome! In this session, we'll be tackling LeetCode problem number 1475, final prices with a special discount in a shop. This problem challenges us to calculate the final prices of items after applying a specific discount rule. It's a great opportunity to practice array manipulation and improve your problem-solving skills. Let's dive right in and explore the details. The problem final prices with a special discount in a shop revolves around an array of integers called prices. Here, each element in the array represents the price of an item in a shop. The unique feature of this problem is a special discount rule. When you purchase an item, you may receive a discount based on the price of another item. Specifically, to calculate the discount for the ith item, you look to the right of it in the array. The discount is equal to the price of the first item you find, moving rightward, which is less than or equal to the price of the current item. If no such item exists, you don't get any discount. The goal is to return a new array where each element represents the final price of the corresponding item after applying this discount rule. Let's break this down with an example. Consider the input prices array, 8, 4, 6, 2, 3. For the first item with a price of 8, the first item to its right that has a price less than or equal to 8 is 4. Subtracting this discount, the final price for the first item becomes 8 minus 4, which is 4. For the second item, priced at 4, the first item to the right with a price less than or equal to 4 is 2, so the final price is 4 minus 2, giving us 2. This process repeats for each item. For the third item, priced at 6, the first valid item to the right is 2, so the final price is 6 minus 2, which is 4. For the fourth item, priced at 2, there is no item to the right with a price less than or equal to 2, so the price remains 2. Similarly, for the fifth item, priced at 3, no valid discount exists, so the price remains 3. The output for this input array is 4, 2, 4, 2, 3. Now consider another example with the input prices array, 10, 1, 1, 6. For the first item, priced at 10, the first valid item to the right is 1, so the final price is 10 minus 1, which gives 9. For the second item, priced at 1, the first valid item to the right is also 1, so the final price is 1 minus 1, which results in 0. For the third item, also priced at 1, there is no item to the right with a price less than or equal to 1, so the price remains 1. Finally, for the fourth item, priced at 6, no valid discount exists, so the price remains 6. This means the output for this input is 9, 0, 1, 6. Another illustrative example is the input array, 5, 3, 2, 1. For the first item, priced at 5, the first valid item to the right is 3, so the final price becomes 5 minus 3, which is 2. For the second item, priced at 3, the first valid item to the right is 2, giving a final price of 1. Similarly, for the third item, priced at 2, the first valid item to the right is 1, so the price reduces to 1. Finally, for the fourth item, priced at 1, no valid discount exists, so the price remains 1. The output in this case is 2, 1, 1, 1. It's important to consider edge cases for this problem. For instance, if the prices array contains only one element, there are no items to the right, so the final price is simply the same as the input price. Another case arises when all elements in the array are the same. Here, each item will always have the same discount applied, resulting in consistent reductions across the array. Finally, if the prices are arranged in strictly descending order, no item will have a valid discount because no item to the right will ever be less than or equal to the current item's price. In this scenario, the final prices remain identical to the input prices. These edge cases help ensure that the solution is robust and handles all possible scenarios effectively. To solve the problem of determining the final prices with a special discount, we need to understand the given rule. For each item in the prices array, the discount is determined by the first subsequent item that is less than or equal to the current item's price. If no such item exists, the discount is 0. A straightforward way to address this is the brute force approach. The idea is simple: iterate through each price in the array and, for every item, look at all the subsequent items to find the first one that meets the discount condition. Once found, the discount is applied by subtracting the smaller price from the current price. If no valid item is found, the price remains unchanged. While this method is easy to implement, it requires nested loops, leading to O(n)² time complexity for an array of size n. Because we're not using any additional structures, the space complexity is 1. However, this approach becomes inefficient for larger datasets due to the quadratic growth in operations. To improve on the brute force approach, we can use an optimized method with a monotonic decreasing stack. This technique helps efficiently track potential discounts as we iterate through the array. Here's how it works. We start with an empty stack and process each price one by one. For the current price, we check the stack to see if it holds indices of earlier prices that are waiting for a discount. If the top of the stack corresponds to a price greater than or equal to the current price, we pop it from the stack and apply the discount by subtracting the current price. This ensures that each price gets resolved only once. After resolving discounts, we push the current index onto the stack, indicating that this price may need its discount resolved later. By the end, any remaining indices in the stack represent items that don't qualify for a discount, so their prices remain unchanged. This approach reduces the time complexity to n, because each index is pushed and popped at most once. The space complexity is n, due to the stack, which, in the worst case, could grow to the size of the array if the prices are strictly increasing. The monotonic stack approach is the strategy we chose for this problem because it is both efficient and straightforward. With a linear time complexity of n, it is well suited for large input sizes, and the logic aligns naturally with the problem's requirements. Compared to the brute force method, which is simple but computationally expensive, and the sliding window technique, which is more complex to implement, the stack-based solution strikes the right balance between clarity and performance. One key insight that makes this approach so effective is recognizing that a stack can systematically track unresolved discounts by focusing on the first smaller or equal price for each item. This eliminates redundant comparisons and unnecessary operations, making the solution not only faster but also more elegant. Ultimately, the monotonic stack provides a scalable and intuitive way to solve the problem within optimal time and space constraints. To solve this problem, we need to compute the final prices of items in the prices array by applying a specific discount rule. The rule states that for each price at index I, the discount is determined by the first subsequent price, at some index j where j greater than I, that is less than or equal to prices, I. If no such price exists, the discount is simply 0. The final price is then calculated as prices, I, discount. The simplest way to approach this is through a brute force method. For each item in the array, we iterate through all subsequent items to find the first valid discount. This involves initializing the length n of the array and looping through each index I from 0 to n1. For each I, we start with a discount of 0 and iterate through the array from I plus 1 onward. If we find a price that satisfies the condition, we apply it as the discount and stop the search for that item. However, this approach has a time complexity of n superscript 2, since for each element, we potentially iterate through the remaining elements in the array, leading to inefficiency for larger arrays. To address the inefficiency of the brute force method, we turn to an optimized approach using a monotonic stack. This approach reduces redundant iterations by leveraging a stack to track potential discounts in a single pass. The process begins by initializing an empty stack that will store the indices of prices in a decreasing order. We then traverse the array from left to right. At each step, while the stack is not empty and the price at the top of the stack is greater than or equal to the current price, we pop the top index from the stack. This allows us to calculate the discount for the item at that index, using the current price. After handling any necessary pops, we push the current index onto the stack. Once the array traversal is complete, any remaining indices in the stack correspond to items that receive no discount, so their final prices remain unchanged. This method is efficient, with a time complexity of n, as each element is pushed and popped from the stack no more than once. The stack-based approach is efficient because it minimizes redundant work. Instead of repeatedly iterating over the same elements as in the brute force method, the stack dynamically updates to track the next valid discount candidate for each item. By maintaining a monotonic decreasing order, the stack ensures that the most recent index in the stack always corresponds to the next potential discount. This method also handles edge cases effectively. For example, if the array contains only one element, the result is simply that element, as there are no subsequent prices to apply as a discount. If all elements are in increasing order, no discounts are applied, and the final prices remain the same as the original. On the other hand, if the prices are in decreasing order, each item except the last will have a discount equal to the next item's price. The stack itself is a crucial data structure here. It is used to store indices of prices, maintaining a monotonic decreasing order. This ensures we can efficiently find the next smaller or equal price for each item. The key operations for the stack include pushing the current index onto it and popping indices when a smaller or equal price is encountered. The push operation adds the current index to the stack, indicating that this item is a candidate for applying a discount to subsequent items. On the other hand, the pop operation is triggered when the price at the top of the stack is greater than or equal to the current price. In this case, we pop the top index from the stack and compute its discount using the current price. This behavior is captured in the pseudocode for the optimized solution. First, we initialize the stack and create a copy of the prices array to store the final results. We then iterate through the array. For each price, we check if the top of the stack represents a price greater than or equal to the current price. If so, we pop the index from the stack, calculate the discount, and update the result for that index. After processing the stack, we add the current index to the stack. Once the traversal is complete, the final array contains the adjusted prices, or discounts have been applied where applicable. This efficient process ensures that each element is handled in linear time. Let's walk through an example to see how the algorithm works in practice. Suppose the input array is prices equals 8, 4, 6, 2, 3. We start by initializing an empty stack and a result array, which is initially a copy of the input array, 8, 4, 6, 2, 3. At the first index, I equals 0, we push 0 onto the stack, as no discounts can be applied yet. At I equals 1, the current price is 4, which is less than the price at the top of the stack, 8. We pop 0 from the stack and calculate the discount for prices, 0, as 8, 4 equals 4. We update result, 0, to 4, then push 1 onto the stack. At I equals 2, the current price is 6, which is greater than the price at the top of the stack, 4, so we simply push 2 onto the stack. At I equals 3, the current price is 2. We pop 2 from the stack and calculate the discount for prices, 2, as 6, 2 equals 4. We update result, 2, to 4. We then pop 1 from the stack and calculate the discount for prices, 1, as 4, 2 equals 2, updating result, 1, to 2. Finally, we push 3 onto the stack. At I equals 4, we push 4 onto the stack, as no further discounts can be applied. This completes the iteration. After processing all elements, the stack contains indices of items that had no applicable discounts, so their prices remain unchanged. The final result array is 4, 2, 4, 2, 3. Analyzing the complexity, the time complexity is O(n), since each element is pushed and popped from the stack at most once. The space complexity is also O(n), due to the stack. This makes the optimized approach highly efficient, even for larger input arrays. In conclusion, the final prices after applying the discount rule are 4, 2, 4, 2, 3. By using a monotonic stack, we've achieved a significant improvement over the brute force method, solving the problem in linear time while maintaining clarity and efficiency. The provided Python implementation solves LeetCode problem number 1475, final prices with a special discount in a shop using a straightforward approach. Here's the detailed explanation. 1. Initialization. The final prices function takes a list prices as input, representing the prices of items, and stores the length of the prices list for easier access. A new list, result, is created by copying prices using slicing. This ensures we have an editable list to store the final prices. 2. Outer loop, over each price. The outer for loop iterates through each index I in the prices list. This index represents the current item whose final price we are calculating. 3. Inner loop, find discount. The inner for loop starts from the index I plus 1 and iterates through the subsequent prices to find the first discount for the item at index I. The condition prices, j, equals prices, I, checks if the price at index j is less than or equal to the current item's price. If a valid discount is found, the corresponding value in result, I, is reduced by prices, j. The break statement ensures we stop searching further discounts after finding the first one. 4. Return final prices. After both loops complete, the result list contains the final prices for each item after applying the discount rules. The function returns the result list as the output. ### complexity analysis. Time complexity. The solution uses a nested loop structure. The outer loop runs n times, and the inner loop may run up to n times. In the worst case, this results in n squared time complexity. Space complexity. The space complexity is n, due to the result list which stores the final prices. This implementation is simple and handles edge cases, such as when no discount is found for an item, the price remains unchanged. It is a direct and readable solution suitable for small to moderately sized inputs. This is the Java implementation of LeetCode problem number 1475, final prices with a special discount in a shop. The logic mirrors the provided Python solution, with differences such as type declarations and array handling. The final prices method iterates through the prices array, applying the discount when a smaller or equal price is found in subsequent elements. Java-specific features, such as using clone to replicate the array, are used to maintain clarity and efficiency. Here, we are tasked with finding the final prices of items in a shop after applying a special discount. The discount is determined by looking at the prices of items to the right of the current item. If we find a price that is less than or equal to the current price, that value becomes the discount. If no such price exists, the item keeps its original price. To illustrate, consider the example input 8, 4, 6, 2, 3. The array length is 5, so we initialize a result array as a copy of the input. Starting with the first item, prices, 0 equals 8, we compare it with the prices to its right. The first value we encounter that is less than or equal to 8 is prices, 1 equals 4. Applying this discount, we update result, 0, to 4. Once a discount is applied, we stop checking further elements for this item. Next, for the second item, prices, 1 equals 4, we again look at the prices to its right. The first comparison is with prices, 2 equals 6, which is greater than 4, so no discount is applied yet. Moving on, prices, 3 equals 2 is less than 4, so we apply this as the discount, updating result, 1 to 2. For the third item, prices, 2 equals 6, we compare it with the elements to the right. The first value smaller than 6 is prices, 3 equals 2, so we apply this discount, updating result, 2 to 4. For the fourth item, prices, 3 equals 2, we compare it with prices, 4 equals 3. Since 3 is greater than 2, no discount is applied. Finally, for the fifth item, prices, 4 equals 3, there are no elements to its right, so the price remains unchanged. After completing all iterations, the final result is 4, 2, 4, 2, 3. Now let's look at another example with the input 10, 1, 1, 6. Here, the length of the array is 4, so we initialize result as a copy of the input. Starting with the first item, prices, 0 equals 10, we compare it with the elements to its right. The first value less than 10 is prices, 1 equals 1, so we apply this as the discount, updating result, 0 to 9. For the second item, prices, 1 equals 1, we find that prices, 2 equals 1 is equal to 1. We apply this as the discount, updating result, 1 to 0. For the third item, prices, 2 equals 1, we compare it with prices, 3 equals 6. Since 6 is greater than 1, no discount is applied. Finally, for the fourth item, prices, 3 equals 6, there are no elements to its right, so the price remains unchanged. The final result for this example is 9, 0, 1, 6. Continuing with the explanation, the iterations for the input 10, 1, 1, 6 demonstrate how the process works step by step for each item in the array. For the third item, no discount was applied because none of the prices to its right were less than or equal to the current price. Similarly, for the fourth item, there were no elements to check, so the price stayed the same. This iterative process ensures that we correctly calculate the final price for each item by evaluating only the necessary elements to the right. The result after completing all iterations is 9, 0, 1, 6. This confirms that the algorithm handles cases with no applicable discounts effectively and updates the result array accordingly. Now, consider a scenario where all items have the same price, as in the input, 5, 5, 5, 5. Here, the length of the array is 4, and we initialize result as a copy of the input. For the first item, prices, 0, equals 5, we compare it with prices, 1, equals 5. Since the prices are equal, this value is applied as the discount, updating result, 0, to 0. For the second item, prices, 1, equals 5, we compare it with prices, 2, equals 5, which is also equal to 5. Applying this as the discount, we update result, 1, to 0. This shows that the algorithm handles equal prices consistently by applying the first applicable discount. For the third item in this example, prices, 2, equals 5, we compare it with prices, 3, equals 5, which is equal to 5. This value is applied as the discount, updating result, 2, to 0. Finally, for the fourth item, prices, 3, equals 5, there are no elements to its right, so no discount is applied, and the price remains unchanged. The final result for this input is 0, 0, 0, 5. This example demonstrates how the algorithm efficiently handles cases with repetitive values, applying discounts appropriately and ensuring correctness even when all values are the same. The process concludes with the calculated result array, which satisfies the problem requirements. The time complexity of the given solution is n squared, where n represents the length of the input array, prices. This is because the algorithm involves two nested loops. The outer loop iterates through each element in the prices array, contributing n iterations, and the inner loop begins from the index just after the current element and continues to the end of the array. In the worst case, the inner loop executes n(i1) iterations for the ith iteration of the outer loop. When we sum up all iterations across both loops, we get the series n1 plus n2 plus 1, which simplifies to n*n1/2. This ultimately results in an n squared complexity. Each operation inside the inner loop, such as comparing prices or performing subtraction, runs an O1 time per iteration. Combining this constant work with the total number of iterations confirms the overall complexity is n squared. In terms of specific cases, the time complexity remains n squared, regardless of the input. In the best-case scenario, the discount for each item is found immediately, meaning the inner loop only executes once for each outer loop iteration. However, even in this case, the overall complexity is still n squared. In the worst-case scenario, no discounts are found, so the inner loop iterates all the way to the end for each item, which also results in n squared. Therefore, the number of iterations in both best and worst cases is proportional to the input size, making n squared the time complexity in all scenarios. Now, for space complexity, the solution requires n. This comes primarily from the result array, which is a copy of the input array prices and is used to store the final discounted prices. Additionally, scalar variables like the loop indices and the length of the array contribute only 1 to the space usage. Thus, the overall space complexity of the solution is n. Breaking down memory usage further, the input array itself is n, but since it is already provided, it does not count as extra space. The output array, however, requires n additional space to store the final prices. Scalar variables, such as the loop indices and the n variable, contribute just 1 space. Combining these, the total space complexity is n. The current solution is a brute force approach, as it checks all possible pairs of prices to identify the first valid discount for each item. While this method is correct, it is inefficient due to its n squared time complexity, especially for large inputs. A more optimal solution involves using a monotonic stack, which maintains indices of prices in decreasing order. This approach allows us to find the first smaller price for each item in 1 amortized time. As a result, the time complexity of the stack-based solution becomes n, and the space complexity remains n due to the stack. Overall, while the brute force method is easier to implement, the stack-based approach is more efficient and preferred for real-world applications or competitive programming scenarios. Let's start by addressing some common mistakes that can occur while solving this problem. One frequent issue is applying the discount to the current item itself instead of the next valid item. Remember, each item should only receive a discount from the next lower or equal price in the sequence, not from itself or any earlier prices. Missteps in loop logic can lead to this mistake. Another common error is using an inefficient brute force approach. While a nested loop to check all subsequent prices for every item might seem straightforward, it results in a time complexity of O(n squared, which is not optimal for larger inputs. Instead, a stack-based approach can reduce this to O(n), making the solution much more efficient. Index out-of-bounds errors are another pitfall to watch out for, especially when handling edge cases like the last item in the array, which has no subsequent prices. Ensuring default behavior, such as setting the discount to 0 when no valid discount exists, can help avoid such issues. Lastly, it's important to fully understand the problem statement. Some may misinterpret next lower or equal price as any lower price in the array, but the discount must come only from future prices in the sequence. Carefully reading the constraints and examples will clarify this requirement. Unnecessary space usage is another common issue. For instance, creating additional arrays or data structures to store intermediate results can unnecessarily increase space complexity. A better approach is to optimize the algorithm to work in place by modifying the prices array directly. Now, from an interview perspective, this problem is designed to test your ability to optimize solutions. It's perfectly acceptable to start with a brute force approach, but you should then demonstrate how to improve it to O(n) using a stack-based method. This problem also falls under the category of next smaller element problems, so recognizing this pattern is key to solving it efficiently. When preparing, make sure to consider edge cases like arrays with strictly increasing prices, where no discounts are applied, or arrays with just one element. Finally, clear communication is critical during interviews. Be sure to explain why you're using a stack and how it helps you efficiently track and apply valid discounts. This clarity of thought will make a strong impression on interviewers. This problem also relates to several others, making it a great opportunity to practice recognizing similar patterns. Examples include LeetCode number 496, which deals with the next greater element I, number 739 for daily temperatures, number 901 for online stock span, and number 503 for next greater element 2. These problems share common strategies involving stacks and monotonic patterns. Now, let's consider alternative approaches to solving this problem. The brute force method involves iterating through each price and checking all subsequent prices to find the next lower or equal value. While this approach is simple and easy to implement, it has a time complexity of O(n squared, which makes it impractical for larger input sizes. On the other hand, the stack-based approach is much more efficient. By using a monotonic stack to track indices of prices in decreasing order, you can quickly determine the next eligible discount for each item. If the top of the stack represents a price greater than or equal to the current price, you can calculate the discount and pop the stack. This method significantly improves the time complexity to O(n), while maintaining clarity and logic. Another efficient approach is to modify the prices array in place to store the final prices directly. This method eliminates the need for additional space and works well within the constraints of the problem. By updating the array as you calculate discounts, you save memory, which can be especially important when working with large datasets. However, while this approach is space efficient, it can make debugging more challenging, as the original input array gets overwritten during the process. This trade-off between space savings and debugging simplicity is worth considering when deciding on your implementation strategy. Overall, being able to adjust your solution to balance time and space complexity is a valuable skill, not just for this problem but for many others in competitive programming and real-world scenarios. Great job! To wrap up, we reviewed the solution to final prices with a special discount in a shop. We highlighted the importance of optimizing for efficiency and discussed key takeaways like handling edge cases and using stack-based techniques. Thank you for joining me, and I encourage you to practice and explore similar problems to deepen your understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!